And well, the subject I'm going to talk about today is actually a byproduct of another analysis on an online going project in order to understand some symplectic capacities of convex sets. However, this project is not finished yet, and along the way, some results came along. So the motivation I'm going to give for the results is a dynamical motivation. So our goal is to understand qualitative properties of rib dynamics on three-dimensional energy levels of a contact type by constructing and analyzing global surfaces of section. So as I said, my motivation is dynamical, but the analysis came from another problem of symplectic topology. I'll come back to that in the end of the talk. And I try to make myself very short. I mean, I try to maybe finish before the time. Okay. So before going to studying the results, I will review a few concepts, which are of course very familiar to most of the audience, to most people in the audience, but maybe not as familiar for some other part of the audience. Okay, so we have a symplectic manifold, and the hypersurface is said to have a contact type if there exists a Liouville field defined around M, around this hypersurface, which is transversal to M, right? So Liouville field, that means it's, I mean, as said already in other talks, this means that it dilates the symplectic form. And a one form on a not-dimensional manifold is a contact form if this wedge is non-zero. And so it turns out that every one form in a not-dimensional manifold comes from the I mean, these definitions are sort of related in the following way. So if you have your hypersurfaces sitting inside the symplectic manifold, and you have your transversal Liouville field, then if you contract the Liouville field with the symplectic form, you have a contact, and restrict this to the hypersurface, you have a contact form, and every contact form arises in this way. Okay. So example, well, star-shaped sets in R2N, right? You have this Liouville field, which is a radial vector field, so everything that is star-shaped is transversal to this guy. Another important example, unit sphere bundles sitting inside cotangent bundles. Okay. All right, and related to a contact form, there is a vector field called the Rab vector field, defined by these equations, which defines a dynamics that is equivalent to the Hamiltonian dynamics of every Hamiltonian function defined this contact manifold, this manifold as an energy level. So Rab dynamics is equivalent to Hamiltonian dynamics on this hypersurface. So, of course, it is well known the question of existence of periodic orbits on such energy levels is historically very important. It started with Einstein in '78, where he looked for Hamiltonian orbits in energy levels which are convex in R2N, and then he proved the existence for these levels, and he made his famous conjecture, which the one that's written there is not the original one, which says that real dynamics always has a closed periodic orbit. So Rabinowitz, '79, proved this conjecture positively. Well, he studied the dynamics on star-shaped sets and also proved the existence of periodic orbits. I wouldn't, well, the results 78 and 79 are almost simultaneous. So in '87, Viterbo proved the original Weismann conjecture by finding closed periodic orbits for hypersurface of contact type in R2n. In 93, so the conjecture as it's written up there, which is not the original one, was only recently solved in 2006 by Taubes for all the three-dimensional version of it. But there was a major breakthrough in 93 by Hofer, where he proves the Weismann conjecture in the three-dimensional case for various three-dimensional manifolds, various three-dimensional contact forms. And I'm going to emphasize on this part of history here. There are also some recent results on higher dimensions by, for example, Albers Hofer, which is just out, using plastic Stufe of Niederkrüger, which is a generalization of the over-twisted disk for higher dimensions. Okay. So here's Hofer's theorem, which I just wanted to state it since we don't see it very often. The Weismann conjecture holds for a three-dimensional manifold M if the contact form is either over-twisted or, well, if it's over-twisted, holds if it's S3, and holds if pi2 is non-trivial. And the proof uses holomorphic curves. And actually in this paper, this 93 paper, that's when holomorphic curves were actually introduced in symplectic, in symplectizations. And, well, the amount of mathematics that came out of this seminal work is like, well, it's tremendous. Well, contact topology, contact homology, symplectic field theory, and many other applications, right? Okay. So what is symplectization? Just to remind you, symplectization of a manifold of a contact form is just R crosses manifold equipped with the symplectic form, even by that formula there, just in case, just to cover people who haven't seen this definition before. So, sorry? Yes, I'm sorry. A is the R coordinate, and lambda is the pullback from the projection to M, right? So how do you study holomorphic curves symplectizations? Well, first I have to have an almost complex structure. And this almost complex structure is related to the contact form in a very special way. So you choose, see here is the contact structure, so you choose some compatible complex multiplication of the contact structure, and then extend to the symplectization by making the R direction, which is sort of the new view direction, map onto the Riemann vector field. So with respect to this J, holomorphic curve symplectizations are defined. And this is sort of natural in the sense that, well, it shows off, at least, well, if you consider the round sphere in R2n. So the standard J, the standard complex J, induces this guy when you use the Liouville vector field to define the symplectization. So doesn't come, or maybe it doesn't come out of nowhere. So Hofer's definition is, and this is a very important definition historically, when people talk about contact or at least the simplest versions of contact homology, these are the curves people use. So finite energy surface, which are the holomorphic curves Hofer considers, are maps from a punctured Riemann surface, which are holomorphic with respect to that multiplication, to J tilde, related to the Riemann dynamics, and has a finite energy. And the energy is the supremum, I mean, you have to, this curve has to have symplectic area bounded uniformly on this family of contact of two forms there, which are almost symplectic, right? Okay. So one of the theorems that Hofer proves in that on his seminal paper in '93 is that the existence of a finite energy surface is equivalent to the existence of a periodic Rip orbit. So he reduced the problem of finding a periodic Rip orbit to the problem of finding a finite energy surface. That's what he does in many cases, in those cases that I stated before. So just to give an idea, I don't know, maybe for people who study symplectic geometry, this is the most standard picture, but for people who are not so familiar with symplectic geometry, this is how a holomorphic curve sort of looks like, right? So you have your domain there, your Riemann surface, you have punctures. Of course, I mean, you have to have punctures because the family of symplectic, I mean, that family of integrals, in order to be non-zero, right? You cannot have them defined on a closed map, on a closed Riemann surface, because they're all exact forms. So this is just to give an idea for people not in the field how do these curves look like. And when you have a puncture, you have a asymptotic convergence of this curve to the periodic orbits. This is just to have a feeling of these curves. Okay, during the 90s, the properties of these curves were very much studied. They're still being studied. And the first people who studied these properties were Hofer, Vysotsky, and Zender in a series of papers where they studied the asymptotic behavior, right? So the behavior of the curve as you approach the puncture. So this is a convergence to the periodic orbit. They also study a bunch of algebraic invariants in order to control how these curves behave. And they also define a Fredholm theory for some curves. I mean, so for a somewhat restricted class of curves. Further purposes were studied by other authors. For example, there is a paper like where a Fredholm theory for summary injective curves is established. I mean, never mind the summary injective means. I mean, they're more general class of curves than embedded curves. Recently, there is a intersection theory of these curves is being developed by Richard Sifrin and many other authors, and I'm certainly going to be unfair here, study properties of these curves and applications. Well, these properties, I mean, the study of these properties allowed for applications. I'm just going to remind a few of them. Hofer, Vysotsky, and Zender, they prove characterizations of the tight tree sphere. I mean, they prove that certain tight contact structures on certain manifolds force the manifold to be the tree sphere. They produce global surface of section for convex energy levels, and I'm going to come back to that. Actually, there is a technical condition which is called dynamically convex. Maybe I'll come back to that as well. So they construct systems of transverse sections for the Rip flow on the tree sphere, on the tight tree sphere, and this work is where the first version of the stretching the neck construction appeared, which gave rise to of course the motivation for the compactness results in symplectic field theory. There are other applications by other people. For example, finite energy foliations on over-twisted contact manifolds, Chris Wendell. Of course, compactness is SFT, of which the first instance appeared in the work of Hofer, Vysotsky, and Zender. And of course, many other applications of this compactness results and this Fredholm theory and of the theory that goes behind these curves. For example, one application that I like to mention, which has a somewhat dynamical motivation, is that on let's say convex sets in R4. There was a paper in 2007 by Bourgeois, Chilibach, and Ekholm that says the contact homology is well defined and that the differential vanishes if and only if the Rip flow has only two periodic orbits. That's somewhat dynamical application of contact homology. So we're going to be interested in constructing global surfaces of section for the flow. What is that? I mean, a global surface of section for the flow is a surface embedded inside your manifold, inside your three-dimensional energy level, let's say. The boundary are periodic orbits. Your surface is transverse to the dynamics. And the flow hits the surface infinitely many times in the future and in the past. So whenever you have a global surface of section, and these guys are very special objects, you can reduce, for example, the study of the dynamics to the return map on this guy. And there are quite interesting applications by Hofer, Wisowski, and Zander, for example. Well, I'll come back to that later. Let me just state their theorem. So they say that, and this was a very famous paper published in the Annals, I think in '98. They say that the boundary of a smooth bounded strictly convex domain in R4, so we're talking about R4, in a convex set here. So this energy level always carries an unknotted orbit for the Hamiltonian dynamics with Conley-Zander index 3, self-linking number -1, and this guy bounds a disk-like global surface of section. Right, I'll come back to the self-linking number. Self-linking number is a contact topological invariant of a transverse knot, in particular of a periodic orbit. So as a corollary, an important corollary, the rip flow has either 2 or infinitely many periodic orbits. I'll explain how this corollary follows. Another corollary, if the rip flow has a knotted orbit, then there are infinitely many orbits. Let me explain how these two corollaries follow, just quickly. So we have this, okay, P0 is the boundary of this disk, which is a global surface of section, right? So the flow hits this guy infinitely many times in forward and past times. It has Conley-Zander index 3, self-linking number -1, whatever that means. And the flow on this section preserves an area form, so we can apply Brouwer's translation theorem and get a fixed point, another periodic orbit, which is of course unknotted because you're talking about S3, right? Have an unknot, something that links once with an unknot is also knotted. So, okay, I think I got ahead of myself. Okay, so here's what I was talking about. So the first return map to this page, to this, let's say to this disk, has a fixed point by Brouwer's translation theorem because the rip flow preserves a finite area form, which is just d lambda, right? Restrict to this page, to this section. And then here's a second orbit. And then, of course, you can delete this orbit and think about the return map on an annulus, on an open annulus, which you obtain by the disk minus this fixed point. Then you can apply Frank's result to achieve 2 or infinitely many orbits. So if you apply Frank's result to the annulus given by removing this fixed point, you have infinitely many orbits. Actually, let me go back. What they construct is much more than a global surface of section. They construct an open book decomposition, actually. So basically, they prove, so the disk that caps the embedded disk that caps this orbit is the projection of a plane in the symplectization, of a finite energy plane in the symplectization. And this plane has special properties. And the fact that the Conley-Zander index is 3 gives you nice properties for this plane. For example, you have a well-defined two-dimensional family of these planes that you can start to perturb. And then perturbing these planes, you have a compactness argument that allows you to close, right, the whole complement of this unknot. So basically gives you a diffeomorphism of the complement of the knot, of the unknot, which is just a solid torus, by flipping the pages like that. So solid torus is the complement, and the section of the solid torus are the closed pages there. Okay, so this is what they prove. So an immediate question that comes out of this construction is how special, right? How special this orbit P0 that they find has to be in order to bound a global surface of section. And I mean, if you follow their construction, their construction is, in fact, the properties. The property of having Alexander index equal to 3 is very special. Actually, that's their source of compactness. And of course, you know, the presence of such global surface of section gives you lots of qualitative information of the flow, about the flow, but you would like to maybe construct other surfaces of section for the flow and extract more other qualitative information about the derivative dynamics. That's my motivation for this work. Later, I'll tell you how this construction came, and it was an accident. Okay. That's the question I'm trying to answer here. How special an orbit has to be in order to be the boundary of a disk, which is a global surface of section. And the property of having Alexander, of course, has to be unknotted. And in their work, they gave no hint of how necessary are the conditions of having self-link number -1 and of having Alexander index equal to 3. They give no hint. Another question is, what other qualitative properties of the dynamics can be derived by such open book decompositions? And that's very much, I mean, this question is still not completely answered. Oh, I mean, there's not even a closed question, right? But there's work to be done here. So the main result I would like to state is a necessary and sufficient condition for a closed rib orbit to be the boundary of a disk, which is a global surface of section. And we actually see that, at least in the convex case, there's got to be at least another geometrically distinct open book decomposition, another geometrically distinct global surface of section for the flow. So here's the theorem. The boundary of a smooth bounded, well, the boundary of this convex set in R4 has the following property. A periodic orbit bounds a disk-like global surface of section for the dynamics if and only if it is unknotted and has self-linking -1. So the condition of being self-linking, of having self-link -1 is easy to check that is a necessary condition. However, this condition of having Alexander index equal to 3 is completely artificial. It plays no role at all. And this condition of having Alexander index equal to 3 is crucial for the compactness argument and for the Fredholm theory. So they use it both in proving compactness for these planes, to prove that you can actually take a page of the open book and flip it around, and also to prove that you have a two-dimensional family, that you have actually a family of pages for this open book. And it's very crucial for their work, and this condition turns out to be not necessary at all. In the case you have such an orbit, you can actually construct an open book decomposition of the complement of this unknot by an S1 family of disks. I should say here that the fact that we are in the 3 sphere, well, it sort of plays no role, plays a very important role, of course, but it plays no role in the deformation theory and in the compactness argument. The problem is where to get your curves from. And so far you can only do that in the 3 sphere. So there is a theorem ready to be applied, which says that if you have a following holomorphic curve, you can actually construct an open book decomposition by, talking about the planar case, right? Talking about holomorphic curves which are spheres. So, so what I'm saying is that there is a theorem already ready to be applied that says that when you have a special curve with such and such properties, you construct the open book decomposition, and these conditions, the conditions that this page is satisfied are actually necessary. The problem is where to get these pages from. So this is technical, I'm going to come into that. So a minor corollary. Well, this is not a minor corollary. This is actually, I think, an important corollary. It just says that in the convex domain, in the boundary of the convex domain, you have the second open book decomposition whose binding is the fixed point of the first return map. So there's at least two global surfaces of section which are sort of transverse. Well, the proof is just a computation of the self-linking number, right? You have the orbit given by Hofer, Vysotsky, and Zander. Then you have this fixed point of the return map here. It's P0, this is P1. So if you can compute the self-linking number of this guy to be -1, then the theorem readily applies. So, okay, that's the picture. So if you compute that self-linking number, and you can pass we can pass of course, the condition of the flow being non-degenerate is useful, but we can always pass to the general case. This happens for any rib flow on the boundary of a convex set in R4. You have these two open book decompositions. Another minor corollary is that if some orbit has self-linking number different than -1, then there are infinitely many orbits. Other constraints, I mean, the existence of these two open book decompositions already gives other constraints on the possible knot types of periodic orbits arising there, but still work to be done here in order to state the theorem. So okay, so since I stated a theorem, and the theorem heavily uses this invariant, the self-linking number. So let me just remind you of what is the self-linking number? What is this guy? So let's consider, for example, an unknotted rib orbit just for simplicity. So, okay, let's think about this, right? This white space inside the orbit as a disk, like an embedded disk capping this orbit. The self-linking number sort of counts, well, before seeing what is the self-linking number, associated to such a surface, you have a characteristic foliation, which is the intersection of the contact structure to the tangent space, right? And then if you put this surface, this disk in general position, then you have a nice Morse-Mail foliation, which is parameterized by the dynamics of some vector field on the surface. And then you have this maybe forces you some tangencies, actually all those forces one. And then when you have a tangency, that means what? That means that the tangent space is equal to the contact structure. You can compare orientations of the disk and of the contact structure, which is naturally oriented by the contact form. And then, well, sometimes they agree, sometimes they don't. So when you see a blue tangency, let's say it's positive. When you see a red tangency, you say it's negative. And then, sorry? I'm sorry. Yeah, so blue and red. What did I say? Okay, so up to an approximation. So then the self-linking number sort of counts the number of tangencies. Well, there is a sign, there is some little signs that have to be worked out there, but in this case, for example, the self-linking number is -3. You can also think of the self-linking number as the sort of the Chern number of the contact structure restricted to the disk, minus it. So if the self-link number is -1, you can always arrange your disk to be like that, right? And then this elliptic tangency there is the source of holomorphic curves, as of course is done by Hofer-Zalski-Zander like 15 years ago. So this is the self-linking number, and the self-linking number being -1 means that the characteristic foliation can be arranged into this position there, and this is actually a necessary condition, right? Whenever you have a rib flow on S3, and S3 here doesn't mean anything, it's not necessary. Whenever you have a rib flow on S3, if you have an embedded disk bounding a periodic orbit, let's say, such that the flow is transverse to the interior, this forces this orbit to have self-linking number -1. This is a necessary condition just for the transversal disk. So this is the self-linking number. So actually the theorem applies to dynamically convex energy levels, and a theorem by Hofer-Zalski-Zander says that energy levels which are convex, which you see as a convex set, boundary of a convex set inside R4, are actually dynamically convex. This is one example of dynamically convex rib dynamics. Another example is given by an observation of Harris and Paternai, which says that, it's well known that geodesic flow on S2 lifts to a rib flow, a tight rib flow on S3, and then when the curvature is 1/4 pinched, then this lift is actually, the flow that you achieve up there in S3 is dynamically convex. So it's another important example of dynamically convex star-shaped inside R4, lifts of geodesic flows with certain curvature conditions. Okay. I could tell you something about the proof. I'm not sure if I should do it. It's very involved, but so what is the idea of the proof? So let's sketch the proof of sufficiency, right? So let's say you have an unknotted orbit. This orbit is sitting inside your convex hypersurface, and it has self-linking number -1. So you have this capping disk, which is an embedding, and then the self-linking number -1 gives you this nice elliptic tangency, which it can be perturbed in order for you to use it as a source of holomorphic disks. And then this is a so-called Bishop family of disks. So just say very quickly what happens here. How do they do it? They have this periodic orbit here. You have this elliptic tangency here. And then you have this Bishop family of disks in the symplectization. Let's think of the symplectization here. And this disk, well, the Fredholm index, the unparameterized Fredholm index is 1, then you can sort of continue this disk family. The two disks go like that. And eventually this is going to blow up. Well, you see, dynamically convex gives you, if you analyze the Fredholm index, dynamically convexity gives you that this disk family cannot stop before. It cannot blow up before. It has to go all the way. However, a complicated intersection argument shows that this disk family cannot touch this trivial cylinder. So there's gotta be bubbling off before you reach this trivial cylinder.
What is this trivial cylinder?
I'm sorry.
Why do you call this cylinder?
Because if you this characteristic foliation can be parameterized by some vector field, right, which can be assumed to be genetic, and then the eigenvalues of that linearization can be made because it's elliptic. Because it's a positive zero. It can be made with real eigenvalues. That's a technical lemma by Hofer. And then,
what is this trivial cylinder?
sorry? Trivial cylinder, we're thinking about the symplectization, right? So this is sitting inside some level in the symplectization, and then you have the cylinder over the orbit. So what they prove is that these disks, when they blow up like that, there's got to be a bubble tree here. I mean, first, the disks cannot blow up before. They blow up as they reach the boundary. You have a bubble tree, whose a bubbling off tree, whose first level is a half-trivial cylinder. Then here you have this orbit P. So here's P, here's P, and here you have a bubble tree. So they argue with Cohn-Lysander indices and Fredholm indices in order to show that this bubble tree actually has to be just a plane. And this plane is already, so they rule out the complicated bubble tree, arguing with the Cohn-Lysander index. They assume the Cohn-Lysander index of P is equal to 3. They use that very strongly to rule out this bubble tree. So this can actually be avoided even if you, one of the crucial points of the proof is that this can be avoided even if the Cohn-Lysander index is bigger or equal than 3. If you do some very careful perturbation of the boundary condition near the periodic orbit. Let me just say that. So this condition is always achieved. And then you have this bubble tree, right? And this disk, of course, the Cohn-Lysander index could be high. Could be much bigger than 3. So the Fredholm index for this disk is possibly very high for this plane. So there's no way you're going to have a nice two-dimensional family of disks there in order for you to start foliating your manifold and construct the open book decomposition. There's no way if you don't control things very carefully. So one thing that can be done is that, how should I say it?
What bubbling is happening in that second picture now?
So bubbling has to happen, right? Bubbling could be complicated. However, they use the Cohn-Lysander index 3 in order to rule out complicated bubble tree because most indices are going to be.
What bubbling is happening in that picture on the right?
So you see.
That's a nice disk here. What is on the right?
Here. Here.
Far right. Right. Extreme right.
Extreme right. That one. This one here. Okay.
So what bubbling is happening there?
You see, these disks are getting. The boundary of these disks are getting closer and closer to the periodic orbit, and they're reaching further and further down the symplectization. That's the bubbling, right? So it's going to be, by compactness, by SFT compactness, let's say, the bubbling
creates that periodic orbit. The bubbling creates that periodic orbit.
So you have a periodic orbit, and then these disks, they go down, they maybe the derivatives blow up, and then you have bubbling off, and it's like some sort of very standard procedure.
Associated with pinching off the sphere?
No, in symplectization, bubbling is associated to stretching a piece of your curve so that it sort of gets asymptotic to a periodic orbit. That's what bubbling is. Okay, so if you can create a page with very special properties, you can actually perturb this page, and then you can create the open book decomposition and the global surface of section. That's what I'm saying. And then how to do this? Well, we have to be very careful with the asymptotic properties at this puncture here. If you analyze very carefully the asymptotic properties of this puncture here, you rule out this complicated bubble tree, you end up with a nice plane with special properties. And let me just say that, the key here is that the approach that can be achieved at this puncture here, at this positive puncture of this part of the bubble tree, is fast. There is associated to every, so you can think of periodic orbits as critical points of the action function. And then associated to a critical point, there is a sort of self-adjoint operator that plays the role of the Hessian. This self-adjoint operator, right, which is sitting on top of a periodic orbit, has a spectrum, right? This spectrum is very related to the Coni's index. And what can be achieved here is that, well, let me just say that, what can be achieved here, I can go into details later if somebody is interested. What can be achieved here is that the asymptotic approach is very fast. You go as fast as you can, you go to the most negative eigenvalue of the Hessian, let's say, for which the Fredholm index is non-zero. It's bigger or equal than 0. Actually, it's bigger or equal than 1. So there's a very fast approach here that rules out the pathology of this bubble tree. And then this family, so then you get a page with nice properties, and then, basically has all the properties of the pages before, of the case when the Coni's index is equal to 3. You actually lower the index. And the fact that this approach is fast, you can, for the Fredholm theory, you can cut down the Fredholm index by putting, an asymptotic weight at a special place of the spectrum. Then you cut down the Fredholm index to an index 2 family of planes, and then out of dynamically convexity, also you get a compactness theorem, a compactness argument, which is nowhere like Hofer-Vysocki-Zender's argument, and then you construct the open book decomposition, right? So just the self-linking number -1 allows us to do all this. Okay, so before I finish, okay, so that's much more than I should say about the proof, maybe. Before I finish, I just want to say that this theorem came out of another project that has nothing to do with dynamics, which is a project about constructing finite energy foliations inside a convex set in order to analyze the value of symplectic capacities of these convex sets. So actually, you see, we have so let's say one wants to study capacities of a convex set is sitting inside R4. Then one wants to study symplectic capacities of these guys. And then, well, over here you have a piece of symplectization sitting inside the boundary, right? And then you have these two finite energy planes with very special properties, and they're linked. There is this Hopf link here, sitting inside the boundary. Let me sort of draw it like that. Okay, this is. Okay, so here's the boundary. You have these two orbits sitting inside the boundary here. One given by Hofer-Vysocki-Zender's global section, and the other given by the first return. And I have these two finite energy planes there. And you see, the idea was to use this sort of like weighted Fredholm theory in order to perturb these planes to planes inside this convex set and build a foliation by finite energy planes inside this convex set by, let me draw the curves here, okay. Let's see, this is P1, this is P0, right? So they're sort of thinking like as a section here. They're going like that, and P1 is going like that. So you have these two planes, let's say, in the symplectization, very near the boundary. Right, it's two planes. And these planes can be perturbed inside the convex set in order to create a finite energy foliation. And this finite energy foliation can be used to study the value of symplectic capacities inside this convex set. However, this work is not completed yet. But that was the original project. And the analysis was already enough to prove the existence of other global surfaces of section different from the ones given by Hofer-Vysocki and Zender. And this is not done, but this analysis has also another corollary, which is an independent proof of the four-dimensional version of two famous theorems of Dusa McDuff about symplectic boundaries. So basically she says that if you have the theorem, her theorem says the following. If you have a symplectic manifold with boundary, let's say all components of the boundary have positive contact type, right? Let me think of symplectic manifold like that. So here's the symplectic manifold. These are components of the boundary. They have positive contact type. So Liouville vector field pointing outwards, both components, let's say, on all components. So she says that if one of these components is equal to S, is contactomorphic to the standard S3, so I'm always four-dimensional here. If one of these components is contactomorphic to the standard S3, then this is the only component. There are no other components of the boundary. This is one theorem. And there is another theorem by McDuff in the same article that says that if this is the case, right? If this is actually the case, so you rule out, first of all, if both are positive, then you rule out this boundary here. And if this is actually the case, here's a symplectic manifold, for manifold. Well, she proves for 2n dimensions. I prove only for 4. I reprove it only for 4. So if this is the case, if one of the boundary components is contactomorphic to the standard S3, and if there are no holomorphic spheres inside, then this manifold is actually diffeomorphic to the 4-ball sitting inside the 4-ball. And this analysis of fast planes, I call these planes with a fast approach, fast finite energy planes. This analysis of fast planes reproves these theorems in 4 dimensions. And the proof is, well, the proof here is sort of clear, right? So we have these 2 orbits which are linked. So of course you can put a contact form here which is dynamically convex, right? The standard S3. So the symplectization here, near the boundary, this neighborhood of the boundary is symplectomorphic to a piece of symplectization that is dynamically convex contact form in S3. So you have these 2 planes, one given by Hofer, Vysotskii, and Zender, and the other given by this analysis. And then the intersection count here is easy to be computed, is equal to 1. And then you can use this intersection point in order to perturb this plane using this weighted Fredholm theory. And then this plane is gonna go inside this manifold. Maybe bubbling off is gonna happen. Maybe there is a sphere here, I don't know. There is a sphere here. Okay, then you forget about the sphere and keep perturbing this plane. And you go on and on until you reach, so eventually you're going to prove that there is a holomorphic curve, whatever it is, through every point of this 4 manifold. And it cannot reach inside this boundary here because of the maximum principle. So you rule out other boundary components. And here is also kind of clear. You have these 2 planes. You assume there are no symplectic spheres here, or well, there are no holomorphic spheres here. And then you keep going. Bubbling never happens. And eventually you're gonna, you see, there is a 2-dimensional family of disks parameterized by a disk. So eventually you're gonna prove that this manifold is, well, it's diffeomorphic to, I don't know, disk cross disk, just a ball. So these are, this analysis of fast planes can be used to, for example, doing this, well, but it can be used for more things, which are on the way, being studied yet. And it can be used for constructing global surface of section as well. I think I should stop here.